So I'm just going to spend this last day of lectures in this unit just going over multi-step synthesis. I'm going to kind of show some common tactics that you can use to approach this. I'm going to do a bunch of examples. And even in our exam review, I'm going to go through more examples of multi-step synthesis. Um, but what I want to emphasize before I get into some common tactics that you can use is you need to know all of the one-step transformations that we've talked about in the previous chapters, in this chapter and the previous ones. And because it doesn't do you any good if you're trying to um, build a synthesis that's reliant on the individual reactions. And if you don't know those individual reactions, then you're not going to be able to do multi-step synthesis. So make it easy on yourself now. Start memorizing. I don't say memorize a whole lot in OChem, but start memorizing those reactions so that you don't have to do that and then memorize the new ones the next chapter we get to, and the one after that, and so on. So literally, it's all you're doing is, again, to use the toolbox analogy, you know what every single tool in your toolbox does, so that when you add a new one in there, it's not like you have to relearn everything. All you have to know is the new tool that you're putting in there. So I just want to kind of give you a quick resource for learning these reactions. Let me switch screens here. So this website, masterorganicchemistry.com, is great in terms of like quickly summarizing series categories of reactions and giving you extra problems to work on. And so just to kind of like highlight, if I scroll down here, I'm going to go to the alkyne reactions unit here, and it's got pretty much all the reactions that we've talked about. And then I want to highlight kind of this table that they put here. And this is kind of a summary of pretty much everything that we've talked about so far this semester. And you look at it and say, wait a second, there's like what, 40, 50 reactions, 55. They're not all different reactions. If you scroll down here, you can see a lot of them are using the same exact reagents or same exact process. And we've talked about this before, where we could do a nucleophilic substitution, say on an alkyl halide, with a whole bunch of different nucleophiles. You just need to know what a nucleophile looks like. So it's not about memorizing like five different reactions. It's the same reaction with a different nucleophile. So let me go back to the notes now. All right, and we can kind of categorize a lot of these or put them together. Like a lot of these here, are going to be our substitutions, nucleophilic substitution. These reactions over here, starting with alkenes, those are our addition to alkenes. We got one down here. This is really simple. What can you do with an alkane? Pretty much the only thing you can do is put an alkyl halide on it. So that makes it really simple. If you're ever starting with an alkane in a synthesis and you want a first step, you have no idea where to go, put a bromine on it to make a bromoalkane. And then on the other side here, again, with this, we have addition to alkynes. And we saw in this unit how similar that process was to addition to alkenes. There's a little bit of variation because now we're dealing with two pi bonds, so we got to worry about stoichiometry and molar ratios. But the processes are very, very similar. And then kind of this last one here, we're dealing with like oxidative cleavage. So adding ozone with a reducing agent or ozone with an oxidizing agent, those sorts of things. So I'm going to do a series of problems. I'm going to kind of break them up so that you don't get, too much video fatigue. So let's take a look at some common tactics that you can use for multi-step synthesis. All right. One of the ones that we've looked at before was moving functional groups. And we did this through a process of elimination and addition. Not necessarily they have to be in that order, but um, it depends on the case. But for example, we have this alkyl halide and we want to get to this alkyl halide, moving that bromine around. So we can't do that in one step, but we can do this in a series of eliminations and additions. Because if I were to do a Zi-Steph elimination, and I want to do a Zi-Steph because that's going to put the double bond closer to where I want to be. And then I follow that up with an anti-Markovnikov's addition of HBr. Now my bromine's closer. Well, I'm going to rinse and repeat. This time, though, I want to do a Hofmann elimination to get the less stable alkene. The reason for that is that puts that double bond right where I want it to be to add bromine to that terminal carbon. And so again, I'm going to do another anti-Markovnikov's addition of HBr. So let's draw on the reagents that will do this. All right, so here we're doing a Zi-Steph elimination, um, but we have a tertiary leaving group, so we're going to use a small, really strong base. So we have a lot of options: hydroxide, alkoxide bases. We could use sodium hydride, so kind of pick your favorite strong, small base, and that will do our Zi-Steph elimination. Now, how do we do a anti-Markovnikov's addition of HBr? Well, we need HBr. Don't forget the peroxides, though, because that will do a radical reaction instead of a carbocation mechanism. Next, we have to do a Hofmann elimination. So remember with that, we need a strong, bulky base. So there's a few that I wanted you to memorize: terbutoxide, DBU, BBN. I'll just put DBU there. That will do the Hofmann elimination. And then I'll do one more anti-Markovnikov's addition of HBr and peroxides to get to my target. And so this is, again, I go over this again because this is a really common tactic when all we're doing is moving a functional group from one place to another. It might not even be the same functional group. Maybe I start with a bromine and, you know, or we go to an alcohol. Okay, part of it is recognizing that the reactions I need are moving one group to another carbon. And so I'm going to do the same process. It's just that maybe my last step isn't involving HBr. Maybe I do an anti-Markovnikov's addition of water, like a hydroboration oxidation. All right, let's do one more example of this. All right, so alcohols, when you're starting with an alcohol, they get very tricky. And here's why. If I want to eliminate that alcohol, if I do the same exact thing I did up here and add a strong base, what is that going to do? Well, first of all, OH is not a good leaving group. Secondly, which hydrogen is more acidic? The one on the oxygen or the one on this carbon that I want to pull off? Say, am I supposed to know that? Absolutely. We'd spend a whole chapter about that. If I throw in a strong base, it's going to go after that alcohol hydrogen and just do a proton transfer. I'm not going to get what I want. So how do I get rid of that OH group then? Well, let's make it a good leaving group. One very common tactic is use tosyl chloride in pyridine, and that converts it into an OTS group, which is a very good leaving group. And then from there, if I wanted to do, nucleophilic substitution, I could substitute with a nucleophile. If I wanted to do elimination, I could. All right, throw a strong base at it, do a Hoffman elimination or a Zysteff elimination. So this is a good tactic if you're starting with an alcohol and you need to get rid of that alcohol or you need to move it. You need to convert that alcohol into a good leaving group. And then I mentioned this before, but just kind of on the side here. If your synthesis has you start with an alkane, the only thing you can do with that alkane is a radical halogenation. And I always pick bromine. Bromine's just better. It's more selective than chlorine. And I talked about why we don't use fluorine and iodine a couple units ago. So that's where I'll stop with this video. I'm going to do more problems in the subsequent videos, so make sure that you follow along.